Now we go into the types of class B amplifier, which is physically implemented. We are going to call it as a class B push-pull amplifier. So the name of the class B amplifier is push-pull amplifier, and it is in this arrangement in such a way that it is called, this configuration is called as a push-pull configuration. See, emitters are connected together. When you are going to tie the emitters of two transistors together, I am going to call it as a push-pull configuration. So you are going to have an input source, and here I am going to have a transformer to isolate the source and my amplifier. This is your source, this is your amplifier, and again you have a transformer to isolate your load. So source, amplifier, load. So you have two transformers on both sides to isolate the amplifier from the source and to deliver maximum power from the amplifier to the load. Okay, at the end of the secondary of second transformer, you will have a load resistance RL across which you can measure the output power. And you see both the emitters are tied up and it is grounded. And you have a VCC connected, which is going to help in biasing your transistor. This VCC is connected to the collector of both transistors to the transformer. So it will help in biasing of the two transistors, Q1 and Q2. And you're going to have resistors R1 and R2, which will ensure that the Q point is exactly on the cutoff region. So this is how the transformer, this is how the class B push-pull amplifier is constructed. Okay, so this is the output characteristics are, you have to consider the output characteristics for the computation of the analysis for the working of this amplifier. See here, this amplifier is going to be in push-pull configuration, which means that when for at a time only Q1 or Q2 is going to conduct. When Q1 is going to conduct, Q2 will not conduct. So when Q1 is going to conduct for a positive half cycle, Q2 will be off. When Q2 is conducting for negative half cycle, Q1 is going to be off. See, my I want signal output should be same as my input. But if you use only one transistor, I will get only positive half cycle, negative half cycle will be completely zero. But I want negative half cycle also. For that only, I'm using a pair of transistors to get back the same input signal. Okay, you see here, when the signal on the transistor Q1 is positive, remember, assume that you are giving a sine wave. Okay, this source is giving a sine wave. So when you are providing a sine wave as input to your thing, positive of the transformer will be positive in the upper half and it is negative in the lower half, because center tap transformer you will have opposite polarity on both ends. When you are going to give a sine wave during the positive half cycle, the base of Q1 will be positive and the base of Q2 will be negative. So naturally, which transistor will be on? Which transistor will be on in this case, Q1 or Q2? Which transistor will be on, Q1 or Q2? Yes, please respond. I have drawn the polarity also. The transformer upper winding has a polarity plus, and lower of the transformer, primary of transformer, you have the polarity as minus. So which transistor will be on? Q1 or Q2?
Q1, sir. Q1, sir.
Q1 is on, Q2 is off. So since Q1 is on, the positive half cycle will be amplified and you will get at the load resistance. Since Q2 is off, I2 will be 0, only I1 will be flowing through the load and you will be getting the amplified positive half cycle. Okay, during the negative half cycle, this polarity will change. The secondary of transformer will be negative, upper portion, and the lower portion will be positive. So now you can say Q1 is going to be off and Q2 is going to be on. So this negative half cycle will be amplified. Actually, you will be getting 180 degree out of phase. So for the positive half cycle, the output will be like this. For negative half cycle, the output will be like this. And I'm using two transistors to get this complete waveform. If you are going to use only one transistor, you will get only either half. Either you will have positive half or negative half. Only one half is possible. Since I'm using two transistors and two collector currents are uniform, that is why you relate now the efficiency. We use 2 into IC, right? That is the reason why I'm using 2IC there in the efficiency expression. Please understand that. Okay. And as the sine wave comes alternatively positive and negative, q1 is on, q2 is off, you get one portion of sine wave. Next cycle q1 is off and q2 is on, you get the next portion of sine wave, and this cycle continues. So the transistor will be amplifying your signal in a very efficient way. But in class a single amplifier, a single transistor was amplifying the entire signal. But in class B, since the transistor is on only for 50% of the time, you need two amplifiers or two transistors to completely amplify your signal. For your positive half cycle amplification, you need one transistor. For negative half cycle amplification, you need one more transistor. Okay, so that is how the explanation of class B push pull amplifier. See, push pull, the word meaning of push pull is when this transistor is pushed into conduction, this transistor is pulled out of conduction. And what is pushing and pulling the amplifiers? The input signal. So input signal will push one transistor into conduction and will pull out the next remaining transistor out of conduction. For the negative half cycle, it pushes the other transistor into conduction and it pulls out this transistor away from conduction. That is why it is named as push-pull amplifier. At the same time, both the amplifiers will not be conducting. So it is like the operation of both the transistors are independent. So Q1 when it is on, Q2 is going to be off. Q1 when it is off, Q2 is going to be on. So that is how this class B push-pull amplifier is working.